All right, today we're pulling back the curtain on one of machine learning's most important, but maybe least talked about techniques, regularization. It is truly the secret sauce that separates a model that just looks smart from one that actually is smart out in the real world.
So let me ask you a kind of weird question. Is it possible for your machine learning model to be too smart? I mean, imagine this. You build a model, you train it, and it gets a perfect score on all your practice data. You're ready to pop the champagne, right? But then you unleash it on new data it's never seen before, and it just completely falls apart. What on earth went wrong? Well, it turns out your model might have been a little too clever, and that's the exact problem we're going to tackle today.
You see, the villain in our story is a sneaky little concept called overfitting. The best way to think about it is like a student who crams for a test. They don't learn the material. They just memorize the exact answers to the practice questions. So yeah, they can ace that specific test, no problem. But the second you ask them a slightly different question, even on the same topic, they're totally lost. They memorized, but they didn't learn. That, right there, is overfitting.
So you've basically got these two cliffs you can fall off of. On one side, you have overfitting. That's a model that's so complex it's basically tracing every little random blip and bit of noise in your training data. On the other side, you have underfitting, where the model is just too simple, it completely misses the real pattern. Our goal, our entire mission, is to find that perfect sweet spot right in the middle.
So, how do we end up in this overfitting trap in the first place? Well, it can happen for a few reasons. Maybe we're just throwing too many features at the problem. Or the model's internal dials, what we call its weights, get turned up way too high, giving way too much importance to certain inputs. You know, you can even just train the model for too long. After a while, it stops learning the real signal and starts memorizing the noise.
But don't worry, because every good story has a hero. And in our story, that hero is regularization. You can think of it as the wise teacher who doesn't just hand the student the answers. Instead, it gives them a framework that forces them to actually understand the concepts. Regularization is what teaches our models to generalize from what they've seen, not just memorize. So, what is it, technically? At its core, regularization is a technique that adds a penalty to the model for being too complex. And it adds this penalty right into the model's main objective, its loss function. Just think of the loss function as a score that tells the model how wrong its predictions are. By adding a penalty for complexity, we're basically changing the rules of the game. We're telling the model, hey, it's not just about being right, you also have to be simple.
To really get this, let's look at a normal model. Without regularization, its goal is super simple. Get the error, the loss, as low as possible. That's it. It will do absolutely anything to shrink the difference between its predictions and the right answers in the training data, even if it means coming up with some ridiculously complicated, overfitted mess of a solution.
And boom, here's where the magic happens. We add a penalty term to that equation. So now, the model has this new balancing act. It has to minimize the error, sure, but it also has to minimize this new penalty. And since the penalty gets bigger as the model's weights get bigger and more complex, the model is now forced to find a simpler solution that still does a good job of predicting.
Now, our hero doesn't just have one move. Regularization actually comes with a whole toolkit of different strategies. The two most famous are called L1 and L2, and each one has its own special superpower. Let's break them down. Okay, here's a quick side-by-side. L1, which also goes by the name Lasso, penalizes the absolute value of the weights. And its superpower, it can shrink some of those weights all the way down to exactly zero. It literally kicks useless features out of the model. On the other hand, we have L2, or Ridge. It penalizes the squared value of the weights. So it pushes weights to get really small, but it almost never makes them exactly zero. This gives the model a ton of stability. So the big headline feature for L1 Lasso is this. It does automatic feature selection. This is huge. If you have, say, hundreds of features and you suspect a lot of them are just noise, L1 is your best friend. It'll just zero out the unimportant ones, leaving you with a clean, sparse model that only uses the most critical inputs. L2 Ridge, though, takes a more democratic approach. It kind of thinks every feature might have some value, so instead of kicking them out completely, it just reduces their influence by shrinking all their weights down. This gives you a more stable, less extreme model in the end.
But what if you want a bit of both? What if you want to get rid of useless features and get that stability? Well, that's where ElasticNet comes in.
It's a hybrid that literally combines the L1 penalty and the L2 penalty. It's super popular because, you guessed it, it really does give you the best of both worlds. Okay, so we've got these amazing tools, but a big question remains. How much of a penalty should we actually apply? I mean, if we apply too little, we still overfit. But if we apply too much, we could end up underfitting. This brings us to what's really an art form, finding the perfect balance. Remember that little lambda symbol from our formula earlier? Well, that's our tuning knob. If we set lambda to 0, there's no penalty, and we're back in overfitting territory. If we make lambda huge, the penalty is so harsh that the model becomes too simple and it underfits. What we're looking for is that just right Goldilocks lambda value in the middle. And we find it by basically just trying a bunch of different values and seeing which one gives the best results on our data. You know, this whole process is a perfect example of a classic concept in machine learning called the bias-variance trade-off. Overfitting is a high-variance problem. The model is just too sensitive to the training data. Regularization works by intentionally introducing a little bit of bias, a thumb on the scale in favor of simpler models, to dramatically reduce that variance. Finding the right lambda is really just about finding the sweet spot in that trade-off. So we've covered a lot of theory, but where do we actually see regularization in action? Let's take a look at some real-world applications, especially when it comes to the most complex models out there today. Neural networks with their millions or even billions of parameters are masters of overfitting. It's so easy for them to just memorize, so they rely heavily on regularization. L2 is so common here that it even gets its own cool nickname, weight decay. But they also use other clever tricks, like dropout, where they literally turn off random parts of the network during training. This forces the other parts to become more robust. Techniques like these are absolutely essential for making these incredibly complex models work reliably. So when should a little alarm bell go off in your head that says, hey, maybe I need some regularization? Here's a quick checklist. If you have high-dimensional data, like more features than data points, regularization is a must. It's also critical when your data sets are small or noisy, and of course, for those super complex models like neural networks. It should be your first line of defense in all these scenarios. But listen, it's not a magic bullet for every single problem. You need to be a little cautious. If your model is already way too simple and it's underfitting, adding regularization is just going to make things worse. And, if you're lucky enough to be working with a massive, super clean dataset, the risk of overfitting might already be so low that regularization isn't really necessary. And all of this brings us to one final big thought. At its heart, regularization is all about a preference for simplicity. In an age where we can build models of almost infinite complexity, it forces us to step back and ask a really fundamental question. In a world of big data and incredibly powerful algorithms, is simplicity itself the ultimate feature? Something to think about.